Hello.
Hey, Luca.
Hey,
Long,
Thomas.
long time no see. How are you?
Well, long time see continuously, but not see on video, which is like the fun, but it's behind closed doors. And now we want to share it. Yeah, you see the sun coming through?
Yeah.
That means the fall is upon us. In the summer, it's all like this, and now it's a bit like tilted like this. And I love the fall because I don't know, maybe my birthday is coming up. And I loved as a kid. I loved when my birthday was gonna happen, and after it happened. So I'm very attached to the fall in the
Yeah.
in the end.
I mean, in Germany, they made a holiday out of it, right?
Yeah. Well, we pack our holiday in the summer, so now finally my kids are going back to school. Eventually, because Italy has this concept of kids being at home for 3 months straight, right? So, like, what do family do? Families do in that time, like, for sure, you take 3 months off and you are with your kid. No, that's not possible, of course, but and yeah, and what else? Talking about kids, my daughter is 16 years old and she's going like third class of high school. And this morning, yeah, you don't know about this. This morning, I gave a talk to a bunch of kids in San Pellegrino. You know the water, San Pellegrino water. Yeah, the place is actually here in the valley, and there was a summer school for like kids, interested kids from all over high schools all over northern Italy, more in the Bergamo area, but they could stay there and sleep there. So they came from outside, and this summer school was great. And I was invited to give one of the final talks, and it was fantastic. I got half an hour of questions. It was amazing. Yeah, we talked about like started from ChatGPT and then showed them what happens in the back. And of course, they're all using it, like, and per using it.
Yeah.
But some of them were really knowledgeable. Some of them didn't have an idea, but they were super interested. And then we talked about like how sometimes life is serendipitous and you need to just do instead of stay and worry. And then
Yeah.
we ended up talking about like the future, the dangers, the opportunities. It was great. Anyway,
Yeah.
um,
I should book you for my son's birthday.
I don't know how they will remember that birthday. Probably, yeah. Not they could have wanted something else for their birthdays, um, but it was great. Like it makes you hopeful.
Yeah.
Anyway, yeah.
That's always like working with young people. Like I'm doing a deep learning thing with a great like charity where they do student like
Mm,
non-computer students learn about data science and deep learning, and it's
hmm.
very cool because
Yeah.
ultimately these people will do things that we never dreamed of doing, right?
Absolutely, yes. Yeah, yeah. So we really sound like old people, Thomas. That's the gist of it. Yeah. And we are. And so in this old people business that we have, it's been some time. We've been working on models for customers, optimizing models using Thunder and a bunch of other things, and the whole stack. Sometimes you need to optimize the models. Sometimes you have like three, four models that need to happen all at once in a pipeline, but you can overlap them, and then you build a server, a customized lit server that will take care of all the orchestration, and you don't necessarily optimize the model much. We've seen a lot lately, and I think the pattern that is showing up is that a lot of companies have great models, and now they have the problem how they run it as a business, and they don't necessarily have all the time in the world to figure out how to do it by themselves. And so, you know, uh, we are proud to help them out with the compute, and then compute plus the
Yeah,
some tricks to make it work better.
right.
And I think in this, and I think NVIDIA calls these people dev techs. and which are the people who are working with customers to optimize the usage of the hardware they sell in the end. And there's a lot of room there in general. And the general sentiment is that Thunder is a good, or could be even better, as a tool for that kind of people, because it gives you X-ray vision into a model, lets you play with the model, and what is fundamental about that is that you see the trace and you manipulate the trace, and this is how you get the perf.
Right.
And so today maybe we will do a refresher on traces in Thunder. So if you want to start doing this as a job, and you want to explore using Thunder to do it as a job, and there's a lot of opportunity if you become an expert to be, a very wanted individual. Then you can start from understanding how the Thunder trace is built and how you can manipulate it. And there is actually a notebook in the Thunder code base that shows exactly that. And the author is one of our friends at NVIDIA, right, Thomas?
Yeah, I think it's Kshitij who wrote the notebook. And it's a absolutely super good notebook. The only thing that is like not so good about it is that Kshitij forgot to take credit of it for it in the notebook itself. Maybe we need to send the PR there.
Yeah, exactly.
Yeah, but obviously, if you contribute this to a larger code base, there always is the danger that it, like goes out of date, and then your name is attached to it yet. But I have a fun story to share too. Like a year ago, I gave a lecture about how flash attention works. And so someone, and I only had a somewhat lame implementation that I used kind of whatever you could get from Numba, and that was kind of limited. And so someone went and said, "Well, yeah, here's C code to accompany the lecture." And,
oh, nice.
Yeah, and so I was reminded of that because, it's great, and two, if you do something like that and create like real valuable material, do put your name on it, because I mean,
absolutely,
it's the work.
Yeah. Maybe we can show it next time.
Yeah.
Yeah, with proper credits, of course.
Yeah, and with Thunder integration, right?
Yeah, exactly. Absolutely. Yeah. So, you're sharing the notebook. So let's see what's the deal here. And, it's a refresher. People that have been following probably know part of these things, but I think it's a muscle that you need to keep. And, the better you exercise the muscle, the better you will do the job. This in measurement.
Right. And so basically it takes apart, and this is one of the things, like you start with the names for everything. So a trace, if you want, is a straight line program. And then it consists, because it's a straight line program, it consists of function calls. And in Thunder, for reasons of its heritage, the functions that are called symbols, and the function calls are then bound symbols, because you like put variables in the, or like relative the things that are passed to the functions in there. And
so you have the functions and the arguments, and this is a bound symbol.
Right.
So a symbol is whatever you will call, and bound symbol is you bind the arguments of that particular call at that point in time to the function, and that becomes a whole thing.
Yeah. And you know the difference between people who know their computer science and just people making it up. And so you have the symbol, you have the args and quarks, and also the output is, of course, part of what is bound. And so those are represented by proxies or constants. Like if you want to put in a tensor, you have a proxy for it. If you want to put in like 2, because the dimension you sum over or whatever. You just put that as an integer if you want. Okay, and so the symbol also has a little bit more detail. And when we've written our own extensions to Thunder last summer, we saw that you needed a meta function that takes the inputs and create as proxies and creates output proxies. And then, of course, at some point you have to make it real, and so you have an implementation like that you have to furnish to. And so if you call a symbol, it will usually call the symbol, the meta function, and then create a bound symbol in the current trace. So Thunder always knows which trace you're looking at, and if you call a symbol, then you call the meta function implicitly, and you add an output to the trace and a bound symbol. So easy enough, but it's like a lot of things to grok, and that's kind of the starting point, and then we dive right into it, right? To confuse you, like Thunder calls the trace a trace CTX, and if I ever do Thunder 2.0, then
that will disappear.
It will be renamed. No more CTX. Okay, and so basically you can JIT compile any function or module, and if you want something simple, you can always go with a function, and you call thunder.jit like we always did, and you can run it, and the output will unsurprisingly be the same as if you call the function itself, right? So no difference here, and that's good. But then you can, of course, print the trace, and basically it converts itself to a string that represents the program if you just have it. And you get the traces, and you get a whole set of traces by asking for the last traces, and this will be the last traces this JIT function has executed. And so
because here, like what potentially is confusing is that the last traces obtains a list of traces, and so last is like the latest traces. Like you need to interpret it that way. No, it's not the last; it's just the more recent traces that the execution of the function generated, right? And then
the traces that the last execution of the function used, right?
Yeah, exactly. And then this will produce a list of traces, and the list of traces goes from the first to the last because there's a set of transformation. We talked about them a lot, and so the execution trace is the last, where this is what it's executed. But if you look at the previous, the first one, it's a different trace that will then not be executed, but transformed until the last, and the last is executed.
Right. So here you see the torch add, which is the implementation. And if I were to do 0 here, you see that it's the L torch, which is Thunder's torch library, right? Or torch language implementation, if you want. So and in between, there's like lots of intermediate things. If you go through auto differentiation, you will have the joint trace that has the forward and backward in one, and then it's going to be taken apart. Okay, but we can go into the trace too, and there we have like a trace as the collection of bound symbols representing the trace program, and also kind of the names that it contains, and also the arguments that you feed to it. But so first you have the bound symbols, and we can show that too. Like, so this is a list, a Python list, and you can see that each item is one of the bound symbols. In particular, this here is one element of the list. So the torch add has what we call subsymbols, and these are here. And return also is a symbol.
Yeah, of course, the printing of each item, like this would error out as a Python, like if you copy paste it, of course, right? So it's a list of things that print themselves that way, just to clarify.
Well, yeah, so you could run it, right? Because it's exactly this here.
No, but I mean the list itself, the
yeah.
interpreter would choke, right? Because there's a comment and blah, blah, blah.
Yeah, well, you need to join the strings, right?
Yeah, for sure.
Basically, the core of the program is just that symbols printed in order, except that there's annotations that we also print. Those can be on the bound symbols. So if you look here, bound symbols to header. Well, 2 was not the right one. Oh well. It sounded like it would have something here, and it should have something, right? So 2. Yeah, I don't know. Somehow
go back and check. Yeah,
knows how to do it, and I don't. Okay, we also have the names, which are basically all the intermediate tensors. And here you can see a thing that is kind of tricky. There are names here like T0, T1, T2, T3 that don't actually appear in the trace. So our bookkeeping is not ideal here. And this is like, you need to avoid name collisions because the contract here, the implicit contract, and we only recently added checks for it that are optional. The implicit contract is that any given proxy name has, or a proxy has a unique name, and any given proxy has one producer. This is also like the reason why we have these bound symbols that are at the beginning, which show up as the comments. So if you look at what the symbol is, it's called sym. It's called unpack trivial, and this basically is a source for the x variable, which is the x proxy, which is one of the arguments. So these are there, but then as the trace gets transformed, we try to reuse names, but that's less than perfect. And here you have that you have old names that are not used anymore. At some point, we probably should clean that up.
But if you print the trace, the zero trace.
What do you mean, a zero?
Not the execution trace, but the trace, the trace.
The initial trace, if you want.
The initial trace.
So let's do it. Initial.
Which is what is produced after the interpreter does its thing, right?
Yeah, here you see.
And there you can see the T0s, the T1s, but then this code will be transformed step by step into other things, and these other things use different names.
Right, and if you show the names, so init trace names, there it's a bit like more cleaned up. It's not perfect because during the recording, Thunder like assigns names very generously, and then we try to match it a bit better to the output code. Like the T1 and T0, those are auto-generated names. And of course, the X and Y come from the Python itself. Okay, but so this is it. And actually, when you follow the tutorial, you have like this list of bound symbols printed more prettily. And yeah, so this is the bound symbol. There also is, and you can also access the keyword args, and you can access the
These are function calls. So you see all the
symbol.
args here and the output. So
Yeah,
all the types that it will produce and so on.
right.
And the
And
shapes. Yeah, we know everything at that point.
you have all that. There is a trick here. Maybe we can show it. That if we look at the add bound symbol, and there we have the subsymbols, right? So in the add bsym, there's the subsymbols, and it's a one-element list that like goes to the first indentation level. And so when you call a symbol, it will actually run the meta function, and the meta function can either like be opaque if it's a primitive symbol, or it can be like this, where it's a compound symbol that is itself can be decomposed, depending on what you want to do. And if you have an executor like the NVFuser, it sometimes wants to grab the primitives here from the decomposition. We're kind of trying to normalize PyTorch a bit more than it is naturally. So, for example, we make the broadcasting explicit, which is useful in some ways, because then you can implement one broadcasting rule and then the addition separately. And so
Yeah.
this is for the code generators.
Yeah, because at this point, like at this point, when you have this operation add, that implicitly broadcasts, and we know it needs to broadcast because we know all the shapes. So at that point, we know exactly what we want to broadcast on what dimensions and to what. So I may when I'm executing this thing, which I haven't decided yet how to execute this thing, I just know that I need to add two things with certain shapes, and so I have multiple routes. One is I can just call torch or something equivalent to torch that will know how to broadcast, or I may call a reduced operation set that has add that is not capable of broadcasting anything, and so I need to broadcast. So I need to have a as granular as possible representation of a computation that is equivalent. So the first line is equivalent to the second and third together. And so at this point, we don't know how this will be executed, but we give you all the options so that when we define that, we decide along the pipeline that we run what will actually execute this add, then we can provide it in the form that is best for that executor, and that will perform the fastest or whatever we want to have as an effect.
Right, and also when you do transformations, you can like do it on the primitives rather than needing to do the full thing. So for example, broadcasting has a backward, and so the backward of broadcasting is summing to the original shape, because basically broadcasting is using the same value multiple times within one tensor. And the derivative of that, if you want, is summing all the derivatives of the various uses. And
this can be checked. You can check it like pen and paper. I suggest whoever is following to do it, because it's very rewarding once you figure it out.
Yeah, and so this is one of the things back in my youth, I sometimes got into arguments on the internet. And so people always insist that you need like more than just the chain rule to do back propagation. And the other thing you need is if you use a thing twice, then you need to sum the gradients from both branches. And
Yeah.
so there are people who write like learned papers with lots of citations how to do it, but that's the only thing you need to know.
Nice.
At least it's it
Yeah.
has never occurred to me like what the other trick is you need. But okay. So this is like the bound symbol and its subsymbols, and we can also take a deeper look at the symbol. So we learned about the meta function and the call method, and let's see what this has been here. So the add bsym has a addition as the symbol, and we can also like zoom in here a bit. We can, for example, run the. Can we run the meta function? No, we can't because it's outside the trace context. So let's cheat here with trace.
No. I mean, it's not cheating. It's teaching.
Oh yeah.
Because we you know that you can't run now, and so you need to create a trace context where this can be actually run.
Right. And
otherwise, it won't work, and you'll be stuck and unhappy.
So I will create a dummy one just to be able to run the meta. And maybe I'll keep this here.
Yeah.
And then we can like have this as a context manager, and we can print it afterwards. Oh,
this is screaming for.
We can like print
like a one-liner.
Okay. So the result is a proxy, and if we like go and print the trace, we see that it doesn't know anything what inputs it should have. But so here's the addition that we had previously too, and it's decomposed like this from calling the meta function.
Yeah. And the proxy, just to remind people, the proxy is just the meta information about a tensor. Basically, right. It carries that. It's not the numbers in it, but the shape, the type, and so on.
Yeah. One thing so I'm surprised what's the difference when I do this. And you see that it has a torch add in addition, because it actually sees the torch add at the beginning if you call the symbol. And so basically by calling the meta function directly, we peeled away one level of hierarchy, right?
Yeah, because because it's an implementation. So the meta already goes one level below to the Thunder Torch library. Yeah.
Okay, so the other thing is that we got this funny tensor proxy here out of it, and so each proxy has a name, and that will be unique to the trace. So here we get T1, which is automatically assigned, right? We don't know anything about it before. And if I like anger the trace a bit and do trace.names, which is just a set currently, I'd probably want to make a dictionary in my next life. But if I claim the T1 name, then you see that it automatically like gets a T2 name. Yeah. Nothing fancy, but good that it happens. Okay, and so you have these proxies, which you can also like access through the args, and these have shapes and name, and they even have methods that then map to torch functions again. But they don't do actual computation, obviously. And one of the things that you sometimes see when there's a gap in the implementation of Thunder is that something gets called with a tensor proxy and says, yeah, I only take tensors, sorry, not tensor proxies. And that means that Thunder doesn't know that it should redirect it to a symbol with meta function and stuff. And so this is then where you need to add a symbol and a look aside for the symbol. Oh yeah, and so here constructing a trace, also we did that already.
Yeah.
And then you have this no signature available,
It's an empty trace. Yeah.
which is,
Nothing in it.
yeah, not very interesting. So it's a bit tricky, but if we have something that has a signature, then it will automatically grab the signature from there. And so you have an empty trace with a name and parameters. Um, this part is also a bit tricky because basically you need to add the same information several times
Mm-hmm.
because you need these unpack symbols, right?
Right.
And
I
so,
mean, you don't do it at home, right? It's just to understand how this
yeah,
happens behind the scenes, right? But
but yeah, so this is like one of the dumbest rules of maintaining consistency is it's best when every information can only be accessed or is only stored once because then
yeah,
you can go like out of
out of
sync.
sync. Yeah.
And yeah,
Because
so
you will shoot yourself in the foot. And so the
yeah,
future
I
you will
certainly
hate the
will.
past you, not you, you in general, like you, the viewer. You know,
Yeah,
your life will be littered with traces of the shootings that you've done on your feet. This will be invariable and it will apply to your programming and your personal life as well. And so you're better off when you can have control, like in this case of designing an API, please avoid that because most of your life you won't have any control, so you won't be able to do much about it. But in this case, you can. Just put the information in one place. Get on with your life.
yeah. Who was that? That was one of the that was Thoreau, right? Simplicity, simplicity, simplicity. I say, let your affairs be 2 or 3, not 100 or 1,000. So
Thank you for the
obviously,
citation.
Thoreau didn't have these fancy GPUs, but he would have been an
Yeah,
awesome programmer.
absolutely.
Lots to learn from the philosophers. Um,
Yeah.
but then maybe we would be happier if we went into the woods more too. Um, but so here Xidich also shows you how to, if you don't call the symbol, you have full control, like you can bind the symbol manually. And
Yeah.
so you specify X, Y, and the output. And this is an alternative way to actually do
Yeah.
things.
This is very, if you need to do advanced things, but it also lets you understand how things actually work. So
Right.
it's a good thing to play with this.
Yeah. And so what he did here is he actually managed to create this ltorch add with the binding.
Yeah.
And the interesting thing here is that because it was a primitive function, the meta didn't record anything. Is it a primitive? No, it's not. So for some reason, which is a mystery, this didn't record anything other than the autometer, than calling the thing directly. But what happens here is that he bound this, or we bound this now manually, and so we don't have the subsymbols here, right?
Exactly. I was going to mention.
And
Yeah.
so this, in a way, is an invalid trace because
Yeah.
uh, there's a convention that either you are a primitive or you need to have subsymbols. And
Right.
so this is a very tricky thing. And indeed, if we like go thunder core trace, no, thunder core trace interpreter, and we can, I think there is there should be a reinterpret function there. Yeah, this is the not rehearsed part that we always include. So you
Of
know,
course. Yeah. That's a tradition. Uh,
Yeah.
Reinterpret trace, right?
Okay. Rerun trace.
Oh, rerun trace. Yeah. Okay.
Yeah. It's like a
Going back to the,
now the
we were
Thunder
saying,
session has reruns.
yeah. No, I mean, I was saying like, I was mentioning before that we sound like old people. And
Yeah.
both of us can't recall the name of the function, so we do sound like old people.
Right. So we had this somewhat inconsistent trace which didn't have the proper thing. And so sometimes when you manipulate the trace, and we showed you ways to manipulate things before, sometimes things can go out of sync. For example, if you change like metadata of proxies and you don't update it in all the right places. And so this rerun trace will actually go through the trace, rerun each bound symbol or the symbol of each bound symbol, and you get the full trace with the subsymbols back.
Yeah.
And so,
of course, you will lose what you set manually if you set anything below it, but it will clean things up for you. Yeah.
And Thunder will make the assumption that like it can do it like that, right? And if you're not respecting that, you're doing something wrong. And so there's another way to do it, like you do the tensor proxies manually, and then you do the ltorch add with the call, and that gives you the full thing directly.
Yeah.
Which is like a super cool tutorial. And so you can break things in Thunder in a few ways. Like I think if you do this, and we can, how can we demonstrate that this thing is broken? So if we go here, and now we want to, can we actually get this as a trace? No. So if I thunder.jit this, will it work? No, it won't work. So this gives an error, assertion error, trace CTX while executing the thing because,
it finds a trace in it.
Right? It should be
exactly.
Python callable.
Still no.
Either.
Oh, yeah. Can you deactivate the provenance?
No. Oh,
it's fun.
Is it? Yeah, the X and Y are tensor proxies from somewhere, and I need to make it proper variables, proper tensors.
There, yeah.
So we copy these. So you can break things in interesting ways, and it would be cool to have like highlights of people breaking traces. So there you get the thing back, and it works as expected.
We basically retraced the Python callable that is generating from a trace, because a trace is a valid torch program. It just straight lined and simplified, but that's what it is. So you can JIT it, which is interesting.
And so you can play with it. And one thing I wanted to show is that if you like actually make this have a derivative, requires rot equals true. And now I need to keep the thing around. So now if you go through the traces, you will find that one of them has
these are all the steps of the transformation traces, and we'll hit upon the autograd one. eventually.
Did I find?
Oh,
Did I not find the autograd one? Oh, so something happened that it's not like requiring the gradient in the output. So here's a breakage. So if I do it like this, I actually get the backward. And now this will have
interesting.
The yeah, so it says created by Dell last used, but and this doesn't have the.
There's an expand one, so it looks like it's already doing the background.
No, yeah, so this here is where the where we have the save for backward. And the trick is that basically the backward of this is not interesting. You just feed the, basically you just feed the inputs back to the output, right? So we need to
maybe make oh
yeah, let's do something slightly more interesting. And there you see, no, this is the forward only too, right?
Yeah.
But it now saves something for backward. But I had hoped that we should see the joint trace somewhere.
Maybe you need to request it explicitly, right? Because there's last backward traces.
Okay, so is it in the backward traces?
Yeah.
No, this is the splitted one, right?
So, yeah. It's already split.
So
did we store it in some different thing?
Maybe there is no. Maybe we don't save it yet, but we should, right?
Yeah, we talked about having everything together, so I need to go back and see when we did do it or not.
Right.
Anyway, yeah, you get the gist. So yeah, we're always, evolving our understanding of the whole system. So between the things that we would have wanted to do and the things that we did, and these, but the traces are there. The backward traces are there. We just want to make it easier for you to access the full thing, because actually something is not trivial in PyTorch itself is looking at the backward and the operation that the backward does. So for sure, this is a plus. If you want to say you have a computation in PyTorch, you want to understand what's going on in the backward and take a look at it, like face the backward. And sometimes, you need to make trade-offs in the backward that you don't do in the forward for efficiency reasons and so on. I think having a very clear representation of the backward is very beneficial. So we have the last backward traces, but then we also want to have a kind of more backward and forward together. And this is what we were missing right now. But you're happy to, we're happy if you, whoever explores and write to us if you don't succeed. And that's it. So I think this is a good reboot. And I think we're going to do something fun next week from our internal, let's say, optimization work, and hopefully we'll do it through Thunder again. And maybe we can disclose something about it in one of the next episodes.
Yeah, super good.
And PyTorch conference is coming up, so that will be fun too. Bye, everyone.
You have a good weekend, everyone.
You too, Thomas. Bye bye.